continuum. They have been like quite rediscovered in photonics in the last decades, roughly. Although you can see that we can actually get back to almost like the fathers of quantum mechanics in terms of this effect. And for you to like understand, let's say the concept is the worst bound states in the continuum comes from the fact that if we just take our classic square wave potential problem, Wigner and von Neumann, they show that if we just modulate this potential in the way that you see, we can find actually like there are like solution of our Schrödinger equation that lies within the continuum of states, like of energies, which means that somehow like they actually completely uncoupled from the radiation and from channels of radiation. And if you want to just see the let's say like the comparison with photonics, then we have to move basically on our non-light cone. And to give you like maybe a bit of more understanding is like you can think about this bond setting continuum as somehow like two coupled resonances coupled to the same continuum, okay? And in this case, like we will have basically like some sort of like coupling between these two, and with some tailoring of the parameters of our system, we somehow can achieve like a-lossy coupled resonances, which would be like very lossy, and you see here. And the other resonance is that we start to like somehow like becomes lossless, like the gamma tends to 0, the Q factor would tend to infinity, because basically like light once out in will never come out. And you can also think about it in between these terms, so like creating basically two modes, one is leaky, one is basically protected by destructive interference. And this bond setting continuum has been like shown in many systems. So it's a wave phenomena. So it's not related to light. It can, not exclusive to light. It can be in acoustic, water, and all the waves phenomena. And here you see like some of the different geometries that has been shown to support these bond sets in the continuum, from arrays of waveguides, one-dimensional photonic crystal, two-dimensional photonic crystal, single particle, single resonant particles. And what I will show you is mostly like the use of two-dimensional metasurfaces, where we basically tailor the geometry of our metasurface to achieve this bound states in the continuum. And as you see here, like basically like we have a bound states in continuum that basically doesn't appear because, of course, like it doesn't couple light. But what we can do is that we can tune these parameters, system parameters, to basically open some radiative channel and then effectively observe like high Q factor resonance, which are usually called quasi-BIC, because BIC itself would be like basically a lossless, of course, ideal state. So in this case, like we use dielectric metasurfaces, so high index dielectric silicon and so on, that are tailored to some sort of like geometry. Now, it's not specific to this geometry. It can be many different geometries, because it's basically simply like a breaking of a symmetry, which usually is this C2 symmetry. And you can think about it in these terms, so that we have some let's say some ellipses, which basically can be represented by a dipolar oscillation of the longitudinal charges and the field. So if we have these two ellipses perfectly parallel, what we have like that two dipole will basically cancel each other out, so creating like a true bound states in the continuum, which means it's a dark state. But what we can do is that we can break the symmetry, in this case with this symmetry parameter, which for our ellipses would be this tilting angle between the two. And if you want to look at in these terms, we basically can think about it that we are creating like an effective dipole moment that can couple to light by just looking at the vectorial sum of these two dipoles moment. And as I told you, like this is indeed like related to this asymmetry, showing this quadratic dependence with the Q factor. And again, like this can be observed in like many different geometries of two-dimensional metasurface that you see there. In our case, like we are, what I will show you like is mainly based on this rods structure. So we have this kind of rods that will give some natural resonances in the array when we look at the transmission of light. And then if we just break a symmetry by simply shorting, basically, reducing the size of one of these two rods, you can see that we actually start to have a new resonance in the spectrum, which is like unrelated to like the natural material itself, but it's actually the so-called quasi-BIC. So like we're actually opening now this radiative channel, creating like a funnel line shapes of our resonance that can be also easily observed to be effectively like related to like the longitudinal excitation of our dipoles resonances. And what is interesting for me, like why I was interested in this BIC, is because of course, like we have, you know, like ultra thin sub-wavelength thickness structures. But the point is that we can engineer like high Q factor resonances and tune them spectrally within the same system. This is achieved by basically tuning the Q factor again through this symmetry parameter that you can see here. So we can tune the Q factor up to infinite values, of course, in theory. But the best that I found interesting was the fact that you can easily like shift this resonance in your spectrum by simply changing the size of your unit cell. So like we just simply scale up or down the size of our, let's say, target unit cell that we were using, and then you can simply like move it fundamentally like in with freedom. So there's no limitation but the material quality, the material properties, thickness of the layers, and so on. And since this is a symmetry protected state, it's exactly the idea that like you don't really relate this to the material properties, but to the symmetry of the system again. And as you've seen this morning, like there is a lot of interest in moving into this bulk TMD nanophotonics, where we want to use indeed like these van der Waals 2D materials for nanophotonic structures. Of course, one of the most interesting features of van der Waals material is the idea that we have no longer like a lattice mismatch where we want to create semiconductor heterostructure, so we can simply stack like layers of materials in any number, form, and of course twist angle and so forth with these van der Waals materials. But beyond the monolayer form, these are also like interesting because they carry basically some of the highest refractive index values for materials in visible ranges due to the fact that we have layered structures plus highly polarizable transition metal atoms. And at the same time, of course, since this layer structure, we can also achieve like extremely large birefringence values, which will help like ideally like in you know, reduction of size of optical components in general. And as an advertisement, we had like a review on these topics recently published, of course, with the idea of using multi-layers van der Waals material for nanophotonics. And I will show you like a first example of coupling basically emitters to these nanophotonic structures. And we started with like tungsten disulfide, so TMD possessing some strong exciton resonances up to room temperature. And what we do is that we simply like exfoliate our 2D material. We find some layer thickness of a few tens of nanometers, so like trying to have like a uniform large flake. And then we just simply pattern them with like top-down lithography, so electron beam lithography and reactive ion etching. You know, they like to define the structure by basically milling away all the excess material around our pillars. And with this work, like we first show that we can somehow like self-hybridize the cavity and material emitter inside the same system. Since like we have like nice excitons in the visible ranges in tungsten disulfide, what we do is that we then created like a large number of these metasurfaces by having also different pixels of metasurface that gives different scaling factor, which again means that we are simply like increasing or shrinking the size of our lattice unit cell, basically, of like a few percentages. And this translates to basically the tuning the cavity across the exciton resonance, as you can see here. And as you can see, of course, we see an anti-crossing effect, which gives values of Rabi splitting around 120 MeV at room temperature. And beyond the fact that we can, of course, control the tuning of the cavity emitter, we also show that by changing this symmetry parameter, we can also tune the Rabi energy itself, of course. This was the first work. It was done again with a material that contains excitons, high index material plus exciton, self-hybridized in the same system. And so we had moved to the use of hexagonal boron nitride, which you might know is a wide bandgap semiconductor, so it's transparent across the visible range, and of course it doesn't have like a very high refractive index, so it's not easy to really engineer like geometrical modes inside the system. The point is that the BICs are not geometrical, they're like symmetry protected, so what we did is that we pattern HBN in different and this is also achieved in a single exfoliated flake. So all these metasurfaces are the same thickness, but of course if we wanted to move into either UV or mid-infrared, we can also like, change the height and push these resonances basically freely in the whole spectral range that our material can support. And this quality factor was around 10 to the 2, but we just basically change a bit the fabrication technique and achieve quality factor above 2000 in a recent work. So meaning that it's of course like just the beginning studying these materials. So fabrication is actually extremely important, as we also seen this morning. Now to get to like the core of this talk, I wanted to basically show you how we can then starting to think to use these HBN metasurfaces as a cavity, so nothing else. And so since HBN is very well known to be an encapsulating material for 2D materials, what we did as a first example was to encapsulate a monolayer, so a single layer of tungsten disulfide, which sustains in plane to the excitons, and then wanted to see the coupling with this quasi-BIC cavity, which, by the way, has negative dispersion in energy compared to like common DBR cavities where you have like a positive parabolic dispersion. And this is quite interesting because it might be also like a new way to engineer exciton polarity on landscapes somehow. And as you see here, this is like the fabrication of the sample. So we simply exfoliate some HBN. In this case, you see here is roughly 60 something nanometer for each layer. Then we encapsulate a monolayer as basically done by almost 15 years by most of the world working on 2D materials. And then we process the stack that you see here through top-down lithography, top-down fabrication, so beam lithography and etching. Then we etch away all the materials around, leaving basically just these blocks of HBN with a small piece of monolayer embedded between them. So there is nothing in between, and you see here like that just we cannot, of course, like resolve this the single unit cell in optical micrograph. And you see here also like a reference patch with no patterning at all, so only encapsulated monolayer. We then move into looking at some spectroscopy. So here is both transmission and photoluminescence emission for a set of this, basically each of these squares. And you can also maybe see that like from this guy to this guy, you have like just a small difference in size. And also like the small one would be the most blue shifted, cavity, and then increasing the size, then we start to basically bring our cavity mode on and over our exciton at 2 eV roughly. Again, you can see that we have anti-crossing. The values of this rapid splitting are around 30 MeV at room temperature. And the interesting part was that in the photoluminescence, something was changing compared to like the normal encapsulated monolayers. And more importantly, we could observe like a new peak appearing at energies below the exciton. And since like we are at room temperature, we have like still like a lot of emission from our exciton. So you see like this line here. But as we come to like almost in zero detuning, that's clearly something happening. We see this peak coming down here, which represents very which matches very well with the cavity modes. And so the idea was like now understanding what is that? So where is this emission coming from? Is it just light channeled through our cavity mode, or is actually like a polaritonic emission? So we went to look at backfocal plane Fourier imaging. In the case of these metasurfaces, on a substrate, we have also not only like this negative dispersion to take into account, but also this guided mode creating diffraction modes in the far field emission. And so you will see that somehow like we will can only observe like our cavity mode within this region. We did some reflectance, and we could observe like our splitting in the reflectance at higher K in this case, and also matching very well with the simulations. And then we went into looking at the photoluminescence emission as a function of the angle, and we could observe that like for positive detunings, since now you have like a negative cavity, like if you were like in the positive regime, positive cavity, like you would have basically no coupling, but in this case, like we now have like some cavity mode arriving up to at these points, which should probably like be related to more of like the diffraction orders. But then the interesting part was when moving at like close to zero and negative detunings, where now like this emission that we were seeing before is actually moving to K equals 0, which represents like basically the minimum in energy of our lower polariton branch, and well, actually not minimum energy, but whatever. And then basically like we could see like indeed like this change in emission from higher K to K equals 0, which is also like usually expected to be indeed like the quasi-BAC emission, which is at normal incidence, so like the 0 order diffraction mode. But like to say if this was actually something related to like polaritonic effectively, like we wanted to see if increasing the power, so increasing the population would lead to some nonlinearities. And to my surprise, we could observe like quite strong shifts in this in K space just by simply increasing the power of our laser. And what I then move into, like we then look at the absorption. So not only the emission, but also the absorption. And we could indeed observe like that up to a certain point, like roughly at this power, we're observing like a collapse of the strong coupling into like a weak coupled or maybe lasing system, which reminded me, of course, a lot about this initial works on quantum wells in microcavities in the 90s, where they were basically like indeed like describing this let's say saturation of the strong coupling and transition to a polariton laser. And since this is done with just like absorption, then we went to look into PL, and we could observe indeed like a very similar effect. So like two peaks where we have a strong exciton as like the upper polariton, basically like degenerate with the exciton at room temperature. But we could observe like then that as we increase the power for like different detunings, we would always see this collapse of the emission into like a single peak, mainly. We then look at the position of the peaks. You see here that they collapse, but also like with a redshift, so mainly related to like a sort of phase state filling. And but the most interesting part was that basically like there was no saturation of the photoluminescence. And this is strange because 2D materials are known to be saturable, basically at certain points through exciton annihilation and more other processes. So in this case, like we were having like an exponential growth. So and then there was no option to increase power due to the laser system that was 80 megahertz repetition rate, so we were not even using that much power, and together with that we were not even focusing highly because we were using low NA objective to capture this light. And then basically to conclude that we then look at the line width of this emission, and we could observe that for like our lower polariton states, we see a reduction in line width, increasing coherent, and so ideally like moving into some lasing or polariton lasing system, basically. And at the same time, we can also observe like that instead, like for the exciton, so like this degenerate upper polariton exciton states, we indeed observe like instead like a broadening as expected. So the two effects plus the exponential like the non-saturation tells us that like somehow like we are going towards some sort of like polariton lasing or maybe condensates in the future. And with this, wanted to of course acknowledge some of the collaborators and some of the of the works, and of course, all of you for your attention. Thanks so much.
For the very nice presentation here.
All right, thanks, Luca. I'm a bit puzzled. So you say you screen the strong coupling gap, and you have a transition to polarity laser, but that one excludes the other thing. You cannot have a screening and then a transition to polarity laser.
Well, let's say
Because
like
you kill the strong coupling on the way.
I mean, we see the. I move on data. So we see this like saturation.
That's normal. I think that's what everybody sees, right? You pump harder and the strong coupling disappears. But that's it.
But then we see it also in emission. So it's the same story. So
but to have a lasing threshold, you have to have a nonlinear increase of the power at the transition, which I guess you don't see.
in this case, if we just this is basically like there is no threshold, basically. So I don't know why, but this seems like there is no threshold in this case. I'm not claiming it's lasing, but what we do is that we could see that like by changing the tuning, then you see the kink. So there is the kink not in this case, but if we just keep on going larger with the tuning. The point is that it was 1 point, so I don't want to.
Okay, I mean, if there is a kink in the power curve, it's maybe a different story, but then you have to check if it's below or above the mod transition, and then you can make an assessment if it's a polarity laser or a condensate or a photon laser once you have crossed the decoupling transition.
Yeah, absolutely. But one thing that I completely forgot to say is that these powers are 3 orders of magnitude lower than every other system of 3D material. So like if you take your microcavity DBRs, like the saturation, the lasing thresholds, and everything that has been said or observed is like 3 orders of magnitude higher in power. Because in all most of the works you use like some kilohertz excitation. Like here we're using 80 megahertz, and on like a large spots, like the powers themselves are extremely small.
All right.
So there shouldn't be this strong mode insulator and so on.
Okay, but you know the exciton density approximately at the threshold?
No, because you know that it's a big problem in like I didn't want to put numbers that I'm not sure. So like for idea is like we wanted to use the fluence, so like saying like this is the power. Then we can discuss how much the metasurface will increase the absorption, and I don't know. That's something that it's harder to tell, but.
Okay, so but still, now is this rather a polarity laser or is it a weak coupling laser? Because that's the part I really didn't get.
That's the part we don't. I mean, the point is that we were like, I was extremely like surprised because we were not expecting anything. The idea of the work was just let's see if it works, and then we started to see this, and everything is been in 2 samples, so it's not one.
I mean, there's a very easy way to figure it out, even if you have no idea about the exciton density. You just put it in the magnet. It will basically solve the complete story instantaneously.
Yeah, we don't have a magnet.
Well, we have a magnet.
Yeah.
Any other questions or comments?
Yes,
Yes,
I have
Anton.
a question. So you excite non-resonantly, right?
No, in this case, no. So
Non-resonantly.
in this case, we're not resonant. We're like a bit high in energy.
Do you have an understanding what's the mechanism for thermalization or?
So I can show you maybe something new because I thought it was too long, the talk, but we actually are moving into like some new work that we recently show. And we started to see how some dynamics is probably affected a lot by this negative. The problem is that everything is still like unclear because there's not many systems that show this negative dispersion with exciton polariton and so on. And at the same time, you have like a sort of saddle point here. So what I show is that I show that we excite along this direction, so you always have this negative, but if you excite on the other, you actually would have a positive. So Sanvito and the group in Lecce, they were discussing a lot about this possible saddle point as a condensation and so on. So the system is complicated and it's new, so we're not really super sure about everything, so the data is my...
Okay, and then a follow-up. So did you try to measure polarization of your light at this regime where you have a superlinear increase of the emission?
Yes.
Is it polarized or is it?
No, it was weakly linearly polarized. Weakly, so it was not.
It's not really polarized.
Fully, but it was. You could see that it was not. It was weakly polarized.
Like okay.
And then of course along the longitudinal direction of the rods.
Okay. And I guess you didn't try to measure G1.
No,
Okay.
not yet.
We have time. We can have a few more questions. Yes, please.
Yeah, this is maybe a very naive question. Thanks for this talk. But was one thing I'm wondering. So this, you have only this monolayers, right? I mean, and you saturate them with excitations. That would, I think, could that change the refractive index? And with that, you actually hold dispersion of your polariton. Is that why you drop out of strong coupling? I didn't understand it.
Yes, but my idea is that I don't like to discuss of monolayers in terms of a refractive index, because there's no I mean, the refractive index of the system is mainly like the HBN related, so I don't think that will not change. The power zero are not so high, so.
Okay.
Any more questions? So maybe I can ask something very quick.
Yes,
So you mentioned this could be a laser of this one. So did you do some G2 measurement to fully confirm this?
No, the point is that no, because the problem is that there is some aging we found out. So these were measured 1 year after fabrication also. But then after many runs, we started to see that there's some problems with this, which is related to the fact that you don't have like the sticking, very strong sticking to the substrate. So if you create structure very high in van der Waals, then we start to like probably collapse onto each other. And so we couldn't then, but the point is that this is also like shown in 2 samples, which I don't have here, so sorry. No, I don't have, but in the paper they then, yeah.
Good. So if no more questions, then let's thanks speak again.
Thank you.
So the last speaker is Jonas Pfister. The title of his talk is Fully Differential Photoacoustics in Complex Nanophotonic Systems. Let's welcome Jonas.
Is working already? Is working already? Yes? Okay. Yes? Good. So, good. Sorry. So, the delay. Sorry, the delay. Oh, everything working. So, first of all, thanks a lot to Florian and Anton for inviting me. Florian and Anton for inviting me. Great to already see really the talks yesterday and great this morning. Already see the talks yesterday. Today I'm going to talk about fully differential photon statistics in complex nanophotonic systems. Differential photon statistics in complex nanophotonic systems, which is work we have been doing like over the last work we have been doing like 7-8 years, I would say. As a kind of general introduction, say. As a kind of general introduction, photons are very nice carriers of quantum information, very nice carriers of light, quantum information. They propagate the same during the propagation in free space. They basically stay the same coherence time, but they have the disadvantage. They have very long coherence time, naturally don't interact with each other. That they naturally don't interact with each other. 500 nanometers of telecom wavelength, 1.5 micron, 500 nanometers of telecom wavelength, 1.5 micron. On the other hand, we have kind of quantum emitters. Super tiny. And on the other hand, we have kind of quantum emitters. So be very visible. So we have quantum emitters that are very visible. Whatever so we have quantum emitters, color centers, quantum dots. Whatever atoms, they are nice because they color centers, quantum dots, non-linearities. They are nice because they are stationary and they're very small. So there's really a disconnect. They are stationary and they're very small. Typically not very strongly coupled. Between these two things, they're typically not very strongly coupled. And the idea is that we can use nanophotonics And the idea is that we can use nanophotonics scale and light confinement, sub-wavelength to enhance light matter interaction and tune this confinement, get the enhanced light matter interaction and tune this and kind of quantum get the functionalities that we want for quantum technology in general. And if we think about quantum nanophotonics devices, we are theorists. And if we think about quantum nanophotonics devices, we are theorists. A lot of different designs that have been proposed in the literature, and we want to be able to describe all of proposed in the literature, and we want to be able to cavities. We can have metal nanoparticles, cavities, crystals, maybe with the metal nanoparticles, photonic crystals, arrays of particle on top, particles. We can have arrays of flakes with structure, particles. We can have HBN flakes with structure, and we can have nanoparticles. What we want to do is to understand really light matter interactions in this complex really light matter interactions in this complex photonic systems in some sense, and be able to describe them correctly in some sense. Which is kind of the first step that we need in order to then actually use them. Kind of the first step that we need in order to then actually use them. Is a quantum description of light matter interactions. Is a quantum description of light matter interaction. And if we think kind of in this complex nanophotonic structures, and if we think kind of quantum optics, traditional cavity QED, Fabry-Perot resonator reflecting my cavity mirrors, then it's relatively straightforward. I have two mirrors, electromagnetic field with boundary conditions. I have the mirrors which give electromagnetic field with boundary conditions, and then usually I don't have to care about too many different modes and losses. And then usually I don't have to care about too many different modes and losses of the mirrors. And the emission is kind of just leakage out. But if I now go into a nanophotonic system where I have a metal nanoparticle, but if I now go into a nanophotonic system where I have metal around with silicon, I send in light from one side, metal around the other side, I really have kind of from one side, all of these on the other side. So I really have kind of broken all of these approximations. So now what I get is that what I want to call my cavity mode, which are really what I get is that what I want to call my cavity mode, which are really coupled to light. Material excitations coupled to light. The fact that my material structure is really an integral part of the light mode. That my material structure is now an integral part of the light mode. Mixed light matter excitations. The photons actually really already mixed light matter excitations. In these cases, I also often get many modes. They overlap. In these cases, I also often get many modes. They overlap. I often have very large material losses with each other. I often have very large material losses. They can be on the order of femtoseconds. So it's really also radiation losses. They can be on the order of femtoseconds. So it's really and I can get not very great separation of time scales. And I can how can we treat this? Fortunately, basically the basic theory of how to quantize light in such complex environments of how to quantize light in such complex environments to a large part has already been developed of Casimir forces and a large part in the community of Casimir forces and Casimir forces. The basic idea is that we take some system development and we separate. The basic idea is that we take some system emitters and we separate it into quantum structures that complex fully with the full nonlinear response that we treat fully with the two-level system response. At least we could treat it as two-level system, but and then we take the cavity that we say is the kind of and then we take the cavity structure that we approximate within electromagnetic structure basically using we approximate within linear response. Basically, and it turns out that within this approximation equations. And it turns out that within this quantize the electromagnetic field in any system. Down how to quantize what I get is a very simple Hamiltonian in any system where I get the emitter Hamiltonian. What I get is a very simple Hamiltonian where I get the emitter Hamiltonian, I get the field Hamiltonian, and I get the light matter interaction. I get the field Hamiltonian and I get the light matter interaction. Gauge, let's call it. At least it's just the dipole operator of the emitters with the electric field. It's just the dipole operator of the emitters with the electric field. And you may say, here it doesn't look like I have any information about the structure. Here it doesn't look like I have any information about to be this kind of my field Hamiltonian actually turns out to be this kind of, well, I have uncoupled modes, these are bosonic operators, but I have one uncoupled mode at every point in space, operators, frequency from 0 to infinity, at every point in space, and at every frequency from 0 to infinity, electric or magnetic excitations, and I have either electric or magnetic excitations, and I have but it's always the same polarization direction. And it turns out the only information about the whole system, and it turns out the only information about the whole system is in this electric field operator that describes the interaction. In this electric field operator that describes the Green's function, the electromagnetic Green's function, basically the Green's function of classical electromagnetic Green's function, so that actually tells me how strongly does each of these infinitely many modes couple to my emitter? Does each of these infinitely many electric field couple to my emitter? We could say, okay, we are done. What's the electric field? Very general way to do this. We could say, okay, we are done. As you may have guessed from what I was commenting, this is not really very useful for what we want to commenting. This is not really very useful for what we want to do, because we have a 4D continuum of modes. We have in space and frequency. We have a 4D continuum of modes. Really is a model with a few modes and frequency. And what we want really is a model with a few modes that I would have to want to describe somehow. Infinitely many modes. And what we have been working on is exactly on ways to do this. What we have been working on is exactly on ways to do this. Of my emitters, the basic principle, whole environment that if I think of my emitters, this whole environment of a forest of harmonic oscillators is basically the only thing that the emitters feel or know about, but really the only thing that they hear when they send in an electromagnetic or know about they send in a signal they hear when they send in an electromagnetic field. They send in a signal and something comes back. But that's really the only information that the emitters know about. They don't know. But that's really the only information that the emitters know about. They don't know all the environment. They just know I'm sitting here. If I send something at this frequency, this is exactly what the Green's function is, phase, etc. And this is emitter therefore only couples in reality to a specific emitter therefore only couples in reality. And what this actually means is that if I look into the dynamics of what this actually means is that if I look out that they're fully determined by of these emitters, it turns out that they're fully determined by now just the Green's spectral density, imaginary part, which is now just at the point of each emitter and each other emitter. So at the point of each emitter and already at the Green's function to look between the positions of the emitter and the Green's function everywhere in space between the positions of the emitter and not kind of everywhere in space to comment. And this so-called cross-spectral density is this so-called closely related to the local density of states, very closely related to the local density of states. The Purcell effect is just familiar with this of the Purcell effect. The Purcell effect is just self coupling to itself, spectral density for an emitter to the self coupling to itself, which is the well-known compared to the free space value omega cube, which is the well-known free space cubic. Or if you want to think in another way, kind of if you're more familiar with quantum. Or if you want to think in another way, kind of descriptions, it turns out the spectral density is also electrodynamics descriptions. It turns out the spectral density is also directly related to the Fourier transform of the autocorrelation function, basically of the electromagnetic field at the position. And the nice thing is now that actually any two linear systems, and the nice thing is now that actually any two linear systems are completely with the same spectral density are completely indistinguishable for the same spectral density. So this is the idea that we want for the emitters. We take this very the idea that we want cloud of harmonic oscillators and we want to replace it by something much simpler. Harmonic oscillators and we want to replace it by something much simpler. From the same response and from the point general concepts that are very useful to understand how we can do this. General concepts that are very useful to understand how we can do this. A single Lorentzian as the spectral density, which we know single Lorentzian resonance, right? As the spectral density, it turns out that the dynamics of an emitter that feels a spectral density, that is the dynamics of an emitter that is actually exactly equivalent. This is a single Lorentzian. This is actually exactly equivalent. This is not solving a Lindblad-Master equation with just a single mode. Solving a Lindblad-Master equation with just a single mode. And the loss rate that is exactly given by resonance kappa. And the loss rate for a single resonance, I already have a perfect mapping. So for a single resonance, I already have a perfect mapping of some complex spectral very simple quantum optics model, the standard to a very simple quantum optics model, the standard James multiple lossy modes, I would just have to use a sum of Lorentzians. And if I had multiple lossy modes, this would also work. Sum of Lorentzians, but it turns out that for the types of systems we're interested in, this is not necessarily. It turns out that for the types of systems we're interested in, this is not necessarily nano-gap antennas. We see the spectral density has some peaks that look like gap antennas. We see the spectral density has some peaks that look like Lorentzians. But then I have a peak, and if I look at like a very broad types of hybrid plasmonic dielectric cavities, where I have some types of hybrid plasmonic dielectric cavities, where I see that the spectral density actually has very cavity, kind of Fano-like shapes, where I don't have just Lorentzians, but really Fano-like shapes, where I don't have just Lorentzians, but really more complex. And then our question was, can we actually find features, something that still looks relatively simple? With something that still looks relatively simple, with a few modes, if I try to approximate this as a sum of very many Lorentzians, because if I try to approximate this as a sum of very many Lorentzians, it becomes very complex. So it turns out that what I can actually do is to say if I take several modes, what I can allow them to couple with each other, I can again show that this is fully equivalent I can again show doing dynamics fully equivalent density. Analytically, by this relatively simple expression, where I just have the inverse given by this relatively simple expression, where I just have the inverse modes of my coupling matrix between the modes. This is not just diagonal as I would usually have. AI, Aj, with couplings between them, omega, Ij have. And they show up in this matrix, and on the diagonal I have a non-Hermitian part that is the losses, and diagonal from the non-Hermitian part that is the losses that come from the So what I'm really doing is replacing this infinite cloud of harmonic oscillators. So what I'm really doing is replacing this infinite cloud of harmonic oscillators with the network. And all I need to do is to find not just independent parameters of this network of modes. And all I need to do is that give me the same spectral density as the emitters actually feel. That give me the same spectral density as the emitters actually feel. Model system where we took a dielectric sphere with, for example, metal nanoparticle model system where we took a dielectric sphere with center. Metal nanoparticle density, which was the black line in the center with classical electromagnetism density, can be black line almost perfectly reproduced electromagnetism with can be just using 20 perfectly modes that are allowed to interact with each other. With since just using 20 modes that are allowed to interact with each other, significantly less than that. 20 peaks here, I'm never going to be able to use significantly less than 0.5 if I want to take the full spectral density that reaches here from 0.5 to 2.5 eV. For example, just to mention, large bandwidth. If you use this quasi-normal mode approach that is somewhat related of another way to quantize the electromagnetic field, somewhat related of another way to quantize the electromagnetic field, a kind of reproducing this whole spectral density over this range, you need many orders of magnitude reproducing this whole spectral density over this range, you need many orders of magnitude taking the modes that my emitter sees, using the fact that I'm just taking the modes that my emitter sees. And also just to mention, if I try to do this with non-interacting modes, and also just to mention, if I try to do this with non-interacting modes, as a sum of Lorentzians with much fewer modes, a fit that is much worse and doesn't reproduce specifically this interference features that is much worse and doesn't reproduce specifically these interference features. So what we have with this method now is really a direct mapping between nanophotonics. What we have with this method now is really a direct mapping between an interesting kind of side result and quantum optics was that. And an interesting kind of side result, the couplings in my Hamiltonian matrix, this omega I really have to do it in a way where the couplings in my Hamiltonian matrix do not omega Ij matrix, and the losses could diagonalize the whole system at the same time. And if they were just be a Lorentz, diagonalize the whole system at the same time. Here, and it would just see that exactly these structures would be a sum of Lorentzians, and here the emitters C I see that exactly these structures in this interference of the emitters C are due to non-commutative, and that means that really for many nanophotonic systems, these kinds of mode interactions are an intrinsic feature. For many nanophotonic systems, these kinds of mode interactions are an intrinsic feature. And that's something that kind of in cavity QED has not really been explored much, because usually you assume that you have independent modes. Just to show that I don't just get access to kind of the dynamics of the emitter, I don't just get access to at least the dynamics of the emitter, I can also calculate the linear field. At least what we show here is if I put the single linear field model system that I mentioned. So what we show here is start the dynamics with the emitter excited, I release the dimension, and I start the dynamics with the emitter excited, I release propagates through the system, and I can really follow this and watch how the electric field propagates and do the system, and I can really follow this coupling or something close to strong coupling, where I see that my emitter where I have population coupling goes down and then comes something close to strong coupling. Wigner Weisskopf or some other coupling formulation and then comes back up again. So with Wigner Weisskopf and some other coupling formulation, I do this for multiple emitters. Also, usually we don't actually want to treat 20 modes necessarily for multiple emitters. Do the fit with the 20 modes. We don't actually want to treat 20 modes necessarily with the emitters by treating them perturbative 20 modes, and then remove all of the ones that are not actually resonant with the emitters by treating them perturbative. Now, why is this interesting? I just want to show a quick example of a work that we did where we used now why kind of mode interactions to implement some example that we call non-Hermitian photon blockade. This kind of mode interactions I'm using to implement similar idea to normal photon blockade, non-Hermitian photon blockade, strong coupling, where basically I'm using similar idea to normal photon blockade, which is if my second excited state was tuned from the send in a light from the laser frequency. So if my second excited state was, then I would suppress absorption of the second photon, and I would see only single laser frequency. So if these two for that I need to go into the strong coupling regime. Then I would suppress absorption of the second photon, and in this case, what we're doing instead is engineering the losses of the strong coupling regime. So what we're looking at is like a plasmonic nanoparticle. In this case, what we're doing instead is engineering the losses of them inside the cavity. But all of them actually within weak coupling, plasmonic nanoparticle, and we show that you can engineer it in such a way that in the first excitation subspace, but all of them actually very weak coupling, sharp mode, and we show that you can engineer it in such a way that in the first excitation subspace, you cannot avoid the losses of the sharp mode, and you get a very broad mode, and it turns out in the second excitation subspace, very efficient, you cannot avoid the losses of the plasmon. And you get a very broad mode, and it turns out that also gives you very efficient photon blockade, and you get very strong cavity. We see single photon emission. Here we show that T2 as a function or even smaller, depending on the specific parameters. Whereas the intensity and the cavity, we see that it really goes down. So here I can use a very strongly non-Hermitian system, a plasmon intensity kind of goes up quite a lot. So here I can use a very strongly non-Hermitian system, everything, and actually use the losses to get something quantum optics that I want, which is a single photon. Kind of run away from, because the losses destroy everything, and actually use the losses to get something that I want, which is a single photon source. We're actually now in contact with several experimentalists. Just to mention, this really requires this non-commutativity of losses and couplings. And again, just to mention, this really requires this non-commutativity of losses and couplings. So I need to use that I have coupled modes. What it does not require, we are still interested in a lot, is to say, up to now we've talked about the dynamics of the emitters. We're interested in, of course, we are still interested in a lot, is to say, up to now we've talked about experimentalists don't measure the dynamics of the emitters, they measure the light that comes out. And what we just did is to say, I don't care about any of the light, don't measure the emitters directly, they measure the light that comes out. Now we want to know how do I actually, what we just did is to say, I don't care about any of the light, I just care about the photons that my system emits. But now we want to know this is in principle actually easy in some sense, because I can get just put access to the photons that my system emits. I can make a filter and experiment. This is in principle easy in some sense, because I can just put a detector somewhere and time, and I can resolve in polarization. I can make a filter and frequency, and I can measure in our theoretical approach, and as far as we know, not in any other theoretical approach for this complex nanophotonic devices, you could actually calculate this. Our theoretical approach, what we came up with is to use actually a very simple trick, complex nanophotonic devices, you could actually in the end calculate detectors, and nothing else but to use actually a very simple trick, some system that is sitting somewhere in this feeling the electric field. And we already know nothing else but, so instead of just using the emitters, some system that is sitting somewhere in this part of the system, we introduce, and we already know emitters, and this is very, very strongly instead of just using the emitters, this method kind of the part of the system, we introduce sensor method fake emitters, and this is very, very strongly inspired by this method, actually from our department. Sensor method and what we do is just place kind of fake emitters where we want the detectors to be that are very weakly coupled to the system. So what we do is just place the dynamics, but I can look at the population, and this tells me how much light that are very weakly coupled to the system, so they don't. And it turns out I can use the dynamics, but I can look at the population, and this tells me how much light second order correlations point in space. And any higher order, it turns out I can use that to get not just the electric field strength, but also the advantages this gives. We looked at the very simple model system, two-level emitter next to a metal sphere, that this works, and what advantages this gives. We looked at a very simple model system, but if I look two-level emitter next to a metal sphere, connecting my emitter to density is actually quite close to a single Lorentzian distance. But if I look at the spectral density, connecting my emitter spectral density is actually a detector at 3 micron distance. Not super complex, but it has oscillations which come exactly because of propagation. Density is actually to the detector. Kind of, and if I look complex time-resolved emissions, which come even in the weak coupling regime, from the compare different methods. And if I look at time-resolved emission, the standard Markovian approximation completely misses. And compare different methods. The retardation effect, we see basically the time that the photons need to propagate from the emission completely misses. The retardation effect, single mode approximation, the photons need to propagate from the emitter. But if I go into strong coupling, and so a single mode approximation of my emitter, I see that kind of okay. Now all of the methods fail. If I go into strong coupling to reproduce the full result, turn up the dipole moment of my emitter, I see that actually really are able now all of the methods fail. very
reproduce
complex
the full
dynamics
result
of photon emission
shown here in black.
in these nanophotonic
So we
systems.
really are able
And
now
to
to
look at the
resolve
more complex
the kind of
system, very complex
fast
dynamics
complex
of
into a
photon
very simple
emission
theorist is just
in
the
these
bigger sphere,
nanophotonic systems, and to
which
look at the
means
bit
that
more
it now
complex
has
system
more than a single
fast
dipole
complex
resonance
into
into a very simple
get
theorist is
access
just
to
the
the
bigger
quadrupole
sphere,
resonance and the hexapole
which
resonance,
means that it now has
and
more
so on,
than
and
a
we now actually
single
put two
dipole
emitters
resonance
next to
you
it
can
and
get
two
access
detectors.
to the
So then we
quadrupole
can look at the
resonance and the
correlation in the
hexapole
emission
resonance and so on, and we
and,
now actually put two emitters
to
next
show
to it
kind of
and
at
two
the
detectors,
frequencies
and
of the
then we
two
can look
emitters
at the
that we will
correlation
use.
in
They
the
are
emission.
exactly set on resonance,
And
with the
just to show
hexapole
kind
and the
at the frequencies of the two
quadrupole emitters that
emission,
we
so
will
we
use,
see
they
the
are exactly
expected
set on resonance
angular dependence
with
here.
the
And
hexapole
what
and
we
the
now calculate is
quadrupole
really the
emission,
now
so we
fully
see the
differential
expected
second order photon
angular
correlation.
dependence here.
So I wrote it down here so you see
And
that
what we now
how many
calculate is
parameters
really
this
the
actually
now
depends.
fully differential
What we
second
actually
order
scan
photon
is now
correlation.
just the
So
angle of
I
the
wrote
two
it down here, so
detectors
you see the fixing the
and how many
frequencies and the
parameters this actually
polarizations.
depends.
And the
What
time
we actually
delay
scan is now just the
the
angle of
bandwidth
the
of all
two
of them, and
detectors.
what we already
fixing
see
the
is that
frequencies and the
here plotting
polarizations
the G2
and
function,
the time delay,
meaning the correlation
and the
between the
bandwidth
emitted
of all of them.
photons. And what we
that
already see
depending
is
on
that
which angles I look
here
into,
plotting
I
the
see
G2
extremely
function, meaning
bunched
the correlation
emission, where
between
G2
the emitted
reaches up to 10
photons,
to the 6,
that depending on which angles I look
bunched
into,
emission, where G2 goes
I
down
see
to the
extremely
10 to the minus
bunched
2.
emission,
So what
where
I see is
G2
really the
reaches up to
photon
10 to the
correlations.
6, or I see extremely
Even in
anti-bunched
this
emission,
very
where G2
simple
goes
system
down
can
to
be
the
very
10
complex,
to the minus 2.
and it's not
So
just
what
a
I see is
single
really
number,
that photon
but it really
correlations,
depends on what you measure, where
even
you
in
measure,
this
and how you
very
filter
simple
your
system can be
emission.
very complex, and it's not just a single number, but it really depends on what you measure, where you measure, and how you filter your emission. Okay.
10
How
minutes,
am I in
perfect.
time? Okay. So now I wanted to switch gears a bit and talk about work that we did recently,
minutes,
where what we looked at
Okay.
is to now extend
now
this
I wanted
method
to switch gears a bit
to
and talk about work that we
periodic
did
systems,
recently,
where
so
what we
arrays
looked at
of
is to now extend this
nanoparticles,
method
or more generally any kind of
to
periodic
systems,
surface,
so arrays
and
of
also assuming that we have a
nanoparticles, or
periodic
more
array of
generally
quantum
any kind of
emitters. So it's not just
periodic meta
kind of,
surface,
spreading
and also
huge amounts of
assuming
molecules
that
on
we
the
have a
surface, but
periodic
having
array of
also
quantum emitters. So
a
it's not
periodic
just
arrays of quantum
kind of
emitters.
the and since now my system is
huge
periodic,
amounts of molecules on the
instead of
surface,
trying
but
to do
having
this brute
also
force, where if I assume that
periodic
it's
arrays
infinite,
is actually
quantum
not really
emitters.
possible.
And since now my
what
system
we
is
do
periodic,
to go into
instead of trying to do this
reciprocal
brute
space,
force, where
which
if I
means
assume
we
that it's
use
infinite,
that
is
now
actually not really
quasi
possible.
momentum is a conserved quantum
what
number,
we do is to
and
go
we
into
can write down now
the
reciprocal
spectral
space,
density as
we
before,
use that now
but not resolved in
quasi-momentum
space,
is a
but
conserved
resolved
quantum
in,
number,
and we can
in,
write down now
reciprocal wave
the
number in
spectral
in-plane
density
momentum
as
K
before,
parallel.
but not resolved in
it
space,
turns
but
out that,
resolved
again, we
in,
can
extend our
reciprocal
few-mode
wave number
model
in in-plane momentum
to,
K
to
parallel.
the same. So we say we
And it turns
resolve
out that
it
again
also
we can
in
explain momentum,
extend our few-mode
and
model
it's basically the same
to,
analytical
to
expression.
the same. So we say
And again
we
can
resolve
reproduce
it also
the,
in plane momentum, the full properties of
basically
the,
the same
of the
analytical
complex
expression.
nanophotonic system.
And again we
that,
can reproduce the
array of emitters
the
fields
full
by
properties
modeling
of
it
the,
with,
of
the complex
this,
nanophotonic system
mode model.
that an array of
we plot
emitters
here now
fields
is for a very simple
by,
system of
modeling
metal
it with
spheres,
this,
silver in
few
this
mode model.
case, with 600
what we
nanometer
plot here now
spacing,
is
and the
for a
sphere
very
radius of
simple
50
system of
nanometers,
metal
with the
spheres
emitters sitting just on top.
silver in this case.
And what we plot here is exactly
with
this
600
K-resolved
nanometer
spectral
spacing
density
and the sphere radius of 50
as a function
nanometers,
with the
kind
emitters
of
sitting just on
momentum
top.
in the unit cell.
And
So
what
we
we
plot
scan
here is
here from
exactly
the
this
M point
K-resolved
to gamma
spectral
to X to
density
M
as a function
kind of
and what you see
momentum
is
in the unit
what
cell.
we
So we
kind
scan
of
here
general
from the
shapes
M
that
point
will
to
be
gamma
familiar
to
to many
X to
people
M,
here, where you see
different
different and what you
diffractive
see
orders.
is you
What
see
we
up
kind
here
of
general
localized
shapes that will
surface
be
plasmon
familiar to many
resonance of
people
the
here,
nanoparticles,
where
and
you
then
see
because they
different
couple to each other,
diffractive
you get
orders.
this surface
You
lattice
see up here
resonances
the localized
that are
surface
kind of
plasmon
hybridizations
resonance of the
between,
nanoparticles, and
diffraction
then because they
orders
couple to each other,
and
you get this
plasmon
surface lattice
resonances.
resonances. One relevant
that
point
are
to
kind of
take into account
hybridizations
here is that what we are
between,
plotting is really the
diffraction orders
spectral density. So this is what the emitters
plasmon
feel.
resonances.
This is not the
One
same
relevant
as the
point to
transmission.
take
If you
into
shine
account
light
here
from
is
the
that what we are
outside,
plotting is really
because
the
you're probing
spectral
it with an
density.
array
So
of
this is what the
dipoles
emitters
field on top of the. This is not the same as the transmission if you shine light from the outside. What we show below here is that with an array of dipoles, move my nanoparticles actually within the unit cell from the point A, which is just on top of the. What we show below here is that if I move my nanoparticles actually within the unit cell, specifically I get just the strongest coupling to my modes spheres to somewhere else. This is I get quite significant changes as well, and specifically I get the strongest coupling to my modes if I'm sitting just on top of the metal gamma point. So we again have I get the strongest coupling to my all of this information if I'm sitting just on top of the system. So and one very interesting thing that we saw here access to all of this information and spectral density the properties of for the surface lattice resonance. One very interesting thing that kind of look like a Lorentzian, but then I have look now at the spectral density for the surface lattice resonance, a mode that is not just a single Lorentzian. My surface lattice resonances themselves are again modes that I have is a mode that is not just a single Lorentzian. My surface lattice resonances losses in are again modes need this non-hermitative resonances are really not just single nice modes. This is losses I think has not really reproduced the dynamics much up to now. We see that kind of surface lattice resonances are really not quantum nice approach, and actually it's very interesting as a talk. But Luca, we looked at up to now a system where we get bounce in the continuum, which is quantum now just using a dielectric nanoparticle approach, and actually it's very with where we talk magnetic dipole resonance. We looked at if you look here now the range frequencies that we look at this system where we get we're looking bounce state in continuum, and we have that exactly again using a electric gamma point because of the symmetry where we have a bounce state dipole resonance where the losses completely disappear. Now the range we get close to it a very sharp small point close to gamma or very sharp mode, and we have that. And what we, here this is again on the left just the spectral density, and what we plot on the right is a way to see the strong coupling when we now where the model the coupling of the emitters with the modes to we get here with the bigs. And we see that we reach a strong coupling regime. And here this is again on the left just polarity density, and what we plot on the right is a way to see the strong coupling when we now model the coupling of the emitters with the modes that we get here with the Bigs crystal, because and we see that we reach this strong coupling regime with the nice periodicity. Polarity on this we look at now the spectral density at one of these cuts, we see that the bound state in the continuum actually is kind of, and we get quite nice Lorentzian in the continuum. Crystal polarity well approximated by a single crystal of array. And if we look in array of emitters with the same periodicity, what we plot here is on the left. If we look at now the spectral density at one of these cuts, we see that the bound state in the really goes down extremely strongly close to quite nice Lorentzian. So this goes formally to zero, well approximated by a single mode. But the coupling between the emitter and the mode, K-space, the emitters are sitting just on top of the mode, is basically independent of black. The decay, so whether that mode is we see that the decay as expected really goes down extremely strongly close to K equals 0. So if you look here, the range goes formally to 0 small, and it's basically a but the coupling between the emitter and the mode, and since the emitters are sitting just on top of the mode, is basically independent of K-space. So whether that mode is linearity of the emitters here really enables the local field very efficient photon pair generation. Look here, the range of wave mixing. If I send in now a laser at one of these frequencies, I can absorb two polaritons. Then we can see and we actually show them polaritons. They scatter with each other to different K. The non-linearity of the emitters here really enables basically very efficient photon pair generation, internal losses, and you get a very, very high effective non-linearity at one of these frequencies. And in a somewhat similar vein, I wanted to quickly mention excite two polaritons. They scatter with each other to different K values, and then get emitted very efficiently because here I basically have a lossless system in terms of internal losses. And you get a very, very high effective non-linearity. Was working on this, and in a somewhat similar now to vein, I wanted to quickly mention somewhat similar setup with an array of nanoparticles. And what we have is actually molecules that have not just an exciton, but also a photon, a phonon, a vibrational transition. Working on this, so that you can. Where the idea was now to this hybrid cavity with somewhat similar setup with an array of nanoparticles, and the surface we have is actually molecules, let's say, that have not just an exciton, you can actually read photon, strong coupling, a vibrational transition, we predict, so that you can, if you use both hybrid cavity visible range, where you get this typical mode in the infrared resonance and the surface lattice resonance, in the infrared range with the in the visible, you can actually reach strong coupling, quadratic cavity dispersion.
both in the
And the
visible
nice thing about
range,
this setup
where you
is
get this typical
that by tuning
lattice
the
resonance
parameters
dispersion,
correctly, you can
and
do it in
the
such a way that the
infrared range with
scattering
the phonons
from
or
the upper
vibrations
polariton
of
to
the
the lower
molecules,
polariton
where you get the typical
can actually be
quadratic, cavity dispersion.
both energy and momentum
strong
conserving.
With
And
the
the nice thing about
polariton
this
and the
setup
phone
is
polariton
that
here
by
in the
tuning
lower
the parameters
dispersion,
correctly,
and then I can
you can do it in such a
efficiently
way that the
do
scattering
nonlinear
from the upper polariton
from
to the
one
lower
polariton
polariton
to
can actually
optical polariton in the upper polariton
both
branch,
energy and
optical
momentum
polariton
conserving
in the lower polariton
with
branch, and
a
an infrared
polariton
phone
in the
polariton
vibrational phonon
here in the
branch.
lower dispersion, and then
It turns out that
efficiently
since I have
do
several
nonlinear
pathways to do
scattering,
this,
I can actually even get very
polariton
strongly
to
entangled
optical
photon pair emissions.
the upper
What I'm plotting
polariton
here is
branch,
the logarithmic
the
entanglement. This is
polariton in
the lower polariton
and
branch,
logarithmic
then infrared
negativity, sorry,
in
which
the
is an
vibrational
entanglement
phonon
measure,
branch.
which basically all of these
And
bright
it
lines
turns out
tell
that,
you
that
since
if
I
you
have
looked at
several
the emission of the
pathways to
phonons,
do this,
I can actually even get very strongly
infrared and the optical
entangled
photons,
you would get
photon
very
pair emissions.
strongly
What I'm
entangled
plotting here is the
photon pair
logarithmic
generation,
entanglement.
and it
This
turns
is
out that this process is also
and logarithmic
extremely
negativity, sorry,
efficient.
which is an
And, I
entanglement
think I'm
measure,
maybe
which
out of time.
basically all of these bright lines
I will
tell
skip
you
this
that
last
if you
page.
looked at the
Okay.
emission of the
Well,
phonons,
if you
feel upset by
the
this infrared and
the
tidal
optical photons,
there is no
you
ultra
would
strong
get
coupling
very
with
strong
photons come and talk to
entangled
me.
photon pair generation.
And,
And it turns out that this process is
I'd be
also
happy to discuss
extremely
this. I'm
efficient.
not going to go through it in more
And
detail.
I think I'm maybe out of time.
And with that, I will
actually
skip this last
thank,
page.
well,
My team
if you
specifically
feel
Francisco,
upset
who
by this
has been
title
collaborator on most
of
of
there
the
is
work
no
I
ultra
showed,
strong
and
coupling with
Antonio,
photons, come and
who we
talk to
also
me.
collaborate strongly with, and my
And,
students and postdocs.
I'd be
And,
happy
thank
to
you all for
discuss
your
this.
attention. I'm not going to go through it in more detail. And with that, I want to actually thank my team, specifically Francisco.
Thank you, Jonas,
who
for the very nice
has
talk.
been- is a
Any
collaborator
comments
on
or
most of the work I
questions
showed,
from the
and
audience?
Antonio, who we also collaborate strongly with, and my students and postdocs. And thank you all for your attention.
So for this last,
Thank you, Jonas, for the very nice talk.
Okay.
Any comments
very
or
nice talk.
questions from the
About the
audience?
results on the space resolve correlations and how you get like a map of
for this
angles
last
with are basically bunch, and you have almost like singular points in space that are anti-bunch. And how do you interpret that? Because
Thank you,
for
very
me,
nice talk.
I mean, in terms
About
of
the results on the
spectral information, I can
space
resolve
handle,
singularities and spectral, but in
correlations and,
space with angle, how you get
how do we
a map of
interpret that you
angles
have this
with
singular
our basically bunch, and you
have
have almost
where
like
you have
singular
anti-bunch.
points in
How
space
do you
that are
understand it? I have
anti-bunch, and
difficulties to understand.
how do you interpret
Most
that?
of
Because
these
for me,
points where there's
I mean, in
strong
terms of
anti-bunching in this
spectral
relatively simple
information, I
example,
can
actually kind of
handle
because of
singularities
geometry,
and
because
spectral, but
one
in
detector
space
becomes
with angle,
basically blind to
how
one
do
of the
we
emitters.
interpret
So
that you
it's
have
in
this
system
singular
we just have two emitters,
emission
and two
where you have
detectors, and if
anti-bunch?
the
How do you
emitter is
understand
polarized
it? I
in
have
the
difficulties to
radial
understand.
direction.
Most of
the
these
detector is
points
exactly
where
the
there's
same
strong
angle.
anti-bunching
It doesn't
is
see that
relatively
one.
simple example.
So then
Actually
it
kind of
becomes
because of
effectively
geometry,
for that
because one
detector, for the
detector
two
becomes
detectors, both of them
basically
have to be in
blind
that
to one of the
configuration.
emitters.
They only see
So
a
it's in
single
this system
photon
we just have
emitter.
two emitters,
and
and
this
two
is
detectors,
basically these
and if
points. That's
the
also why
emitter is
they're
polarized in
narrow
the
this case.
radial direction, and the detector
So
is
this is a
exactly the
relatively
same angle.
simple
It doesn't see that
explanation,
one.
actually. So then it becomes effectively for that detector or for the two detectors,
thanks,
both
this was
of
a great
them have
talk,
to be in that
Johannes. I have
configuration.
two questions.
They
and the
only
first
see
question
a
is,
single
so in
photon.
your approach,
emitter.
you always
This is
take
basically these
dipole
points. That's
as,
also why
as
why they are narrowing
representing the
this case.
emitter. But when you
So
go
this is a
to
relatively
very close to
simple
plasmonic surface,
explanation,
where
actually.
actually also the shape of the, I mean, it is this pico lightning rod thing effect
Thanks,
in
this was a
Baumberg's
great talk, Johannes.
system,
I
for
have
example.
two questions, and the
Would
first
you then
question
have to
is,
reformulate
so in your
everything if you wanna
approach,
go beyond
you
dipole,
always,
or is it just
No, it's
take
actually
the
very
dipole
straightforward
as,
extension.
as
You basically just
representing
go
the
to higher order
emitter?
in the multipolar
But
extension.
when you
and
go to very close to
during
plasmonic
the
surface, where actually also the shape
in the,
of
well, the
I
Maxwell
mean, it is this
equation, we already have it.
pico
Basically, what you
lightning
need is
rod
the
thing
gradient of
effect in
the
Baumberg's
Green's function. We've
system, for
already done it.
example.
We haven't published
Would you then
anything
have
on
to
it.
reformulate everything if you wanna
And
go
actually,
beyond
Carolina
dipole, or is it
Slovik
just
has a very nice paper
actually
which
very
shows all of
straightforward
this.
extension.
You basically
go to
couple
higher
them
order
to
in the multipolar
quadrupole
extension
couples to
and
the gradient of the Green's function.
during the classical
And all the
Maxwell
model
equation?
is
In
the
the-
same.
well, the
Maxwell
It's just
equation
that
we already
instead
have
of
it.
kind of
Basically,
G
what you need is the gradient of
E
the
dot nu, you have
Green's function.
Q
We've
dot
already done it. We haven't published anything.
gradient of
And actually, Carolina Slovik has a very nice paper.
actually in the formalism,
nothing
you basically
fundamental
couple then
changes,
you have to do a bit
the
more work in
quadrupole
the
couples to the
nanophotonic
gradient of the
calculation.
Green's function.
and
thank you.
all the
That's
model
definitely something
is
we
the
have on the
same.
radio.
It's just that instead of kind of
And the other
g dot
question is to
mu,
measure these
e
entangled
dot mu, you have
photons
q
from
dot
infrared and optical. Does it
gradient
also
of
require they have the same
the thing,
loss rate
of the
in
field.
this?
So
Combined
actually in the
cavity?
formalism,
No, this
nothing
doesn't
fundamental
depend on that.
changes.
That means
Measuring
a little bit more
photons in the
work in
infrared
the
in general is
nanophotonic
hard, which is why we
calculation.
actually have a second part where we
That's
show that you
definitely
can
something we have
do
on the
up
radio.
conversion and actually get
And the other
two,
question is to measure
two
these
optical
entangled
photons out that are
photons
still
from
entangled.
infrared
But I
and
didn't have
optical.
time to show
Does
that.
it also
But yeah, in
require they have the
principle, if you
same
can measure
loss
them, if you
rate
have a
in
detector in
this
the infrared and a
combined
detector in the
cavity?
optical, you
No,
this doesn't depend on that. I
Okay,
mean,
so one can
measuring
come out.
photons in the infrared in
Any more
general is hard,
questions?
which is why we actually have a
Yes,
second
from the
part where we
back.
show that you can do up conversion and actually get
During the transfer of
two
macro, I can
optical
ask something
photons
very
out that
quick.
are still
So you
entangled.
mentioned the
But I
nonlinear
didn't
conversion
have time to
efficiency
show that.
could
But
be
yeah, in
very
principle,
high.
if you
So
can
roughly
measure them, if you
how
have a
high
detector
is
in the
high?
infrared and a detector in the optical, you
So
for the example we
Any more
looked at, I mean,
questions?
as usual, you have the
Yes, from the
scaling with
back.
the intensity, but I think we had for this
During the
four-wave
transfer of
mixing
macro, I
a
can
few
ask something
percent
very quick.
in
So you
just
mentioned
a
the
kind of a
nonlinear
very
conversion
dilute
efficiency
sample
could be very high.
at
So
a
roughly
reasonable, very
how
low
high is
pumping
high?
intensity actually. So for
yeah, it would be good to compare with
the example
with
we
the
looked
numbers
at,
you
I mean,
showed
as
to
usual,
see how
you
this
have the
compares. We
scaling
we
with the
haven't done that yet.
intensity, but I think we
Please.
had
Okay, thanks, Johannes.
for this four-wave
Nice talk.
mixing a
I
few
have a question
percent
about this
in
mapping
just a
method.
kind of a very
You-
dilute
you
sample
map the system
at a
to
reasonable, very low
some-
pumping intensity actually.
some
So yeah, it would be good to compare with
Then
the
how-
numbers you showed
how do
to see
you
how this compares.
choose
We
the
haven't
correct
done that yet.
initial condition for
Please.
this
Okay, thanks.
quantum
Johannes, for
system.
the
Nice talk.
Do you
I have
have
a
to
question
restrict
about
it
this
somehow because
mapping
you
method.
basically
that
construct
you,
it from a
map the
classical
system to
from Maxwell's
some-
equations, essentially.
some
Well, so
Lindblad
usually,
equation.
yes, I mean, since we're working in
How-
optical
how do
regime
you
and we
choose the
assume
correct
even room
initial
temperature,
condition
there's
for
no
this
excitations. So it's just the
quantum
ground
system?
state. There's no initial
Do you have to
excitations
restrict
apart
it
from the
somehow
laser that we
because
send
you
in.
basically construct
So
it
in
from
that
a,
sense,
from a
that's relatively
classical,
straightforward.
from Maxwell's
If you go to low
equations,
enough
essentially.
frequency,
Well,
you
so
would have to take a
usually,
thermal bath,
yes,
which up to now
since
we
we're working in
basically always
optical
ignored, but in
regime
principle it's
and
not a
we
huge
assume
difference.
even
Okay,
room
thank you.
temperature, there's no excitations. So it's just the ground state.
Any
There's
more
no
questions?
initial excitations
If
apart
not,
from the
then
laser that we
Let's
send.
thank the two speakers
So in
again.
that sense, that's relatively straightforward. If you go to low enough frequency, you would have to
With that, I
take
give
a
the mo-
thermal bath, which up to now
Yeah,
we
microphone
basically always ignored.
Thanks.
But
A
in
little
principle
announcement.
it's not a
So
huge difference.
lunch is served upstairs as yesterday, same place. Right
more
after
questions?
lunch, we have
If not,
those
then
who sign
let's
up who
thank
want
the
to
two
go
speakers
to
again.
and see low temperature labs in Nanotalo. Please be in the
that, I
lobby
give the
by,
mo-
I would say
Yeah,
1:15.
Thanks.
A little
In the
announcement.
lobby of this
So
building.
lunch is served
And then we go to
upstairs
another
as
building to see the
yesterday.
labs.
Same place.
Then we also have a dinner
right after
today,
lunch, we
starting
have
at 7,
those who sign up who want
actually
to
in
go
the
to
downtown.
and see low
And
temperature
if you
labs
don't
in,
have a
Nanotalo,
ticket yet, please come to
please
Emily
be
or
in the
Leonie
lobby
and
by
they will provide you a ticket.
I would say
And
1:15.
also we're gonna have
in the lobby of this
a
building.
poster award
And then we
ceremony
go to
there,
another
so,
building to see the labs.
please don't miss
Then
it.
we also have a dinner
Perhaps it's your
today,
poster.
starting at 7, actually in the,
Yeah, it's
in the
open for
downtown.
everybody. Yes.
And if you don't have a ticket yet, please come to Emily or Leonie and they will provide you a ticket. And also we're gonna have a poster award ceremony there, so please don't miss it. Perhaps it's your poster.
And just a little side info,
Yeah, it's open
cafeteria,
for
the
everybody.
caterers
Yes,
left
thank
the snacks and coffee out, so if you want anything else, feel free to graze and have a nice lunch. And just a little side info, cafeteria, the caterers left the snacks and coffee out, so if you want anything else, feel free to graze and have a nice lunch.